Hello everyone, welcome to ExamRat. My name is Shatabdi. I'm a second year medical student. So today we're going to be talking about reflection of light. In case if you've missed our previous sessions, you can easily go to our YouTube channel and watch it. They're all for free. Okay, so let's start. Now reflection. The last class was about sound, where we had also talked about the laws of reflection. Why? Because we had somehow compared it with those of reflection of laws of reflection of sound, and we found that both of them were same. So, what are these laws? It says that the angle of incidence is equal to the angle of reflection, and the incident ray, the normal to the mirror at the point of incidence, and the reflected ray all lie on the same plane. Okay, so in simple words, if this is the incident ray, this is the reflected ray, we draw a normal. Normal are supposed to be straight. Sorry. Yeah. So if you just like draw a normal. So now what they are saying is that angle of incidence, angle of reflection, they will always be the same, provided that all the 3 points, even if it does not show in my picture, but trust me, all these points will always be on the same plane. Only then will this law work and this law be proven. Otherwise, you cannot use this law. Okay. These laws of reflection are applicable to all types of reflecting surfaces, including spherical surfaces. So, as long as you have a polished surface, and what does it mean? It means that one part will be reflected, and the, like if this is a mirror, then one side of it will have to be completely opaque and the other side will have to be polished. Okay, this side has to be polished so that no amount of light gets absorbed, all the light will get reflected. So that's why one side has to be polished, which was not the case in law of sound, because sound just required one simple structure in front of it to be reflected. It did not care whether it was polished or rough. But here the prerequisite is absolutely that it has to be a reflecting surface, and when we say reflecting surface, we mean that it has to be polished. Okay. So now we'll talk about formation of image by a plane mirror. Obviously, we have all experienced it in our day-to-day lives, like while getting ready for any sort of function. We always let this be a mirror. Okay. So first we have to talk about something, and that is real image and virtual image. So real image is something that you cannot see, that you cannot, like it will not be seen by you. But on the other hand, the virtual image, you can always see it. So this means that the real image, basically you can take it down on a paper, or we'll discuss about the real image when we come to specifically the image formation by spherical mirrors. For now, just remember this much, that a virtual image you can see directly through your own eyes, a real image you cannot, unless it is taken down artificially through on a piece of paper or something else. Okay. So real images are inverted, whereas the virtual image, like obviously when you see yourself in a mirror, you're always erect, like you're not upside down. So the image formed by plane mirror laws is always virtual and erect. The size of the image is always equal to that of the object. Obviously, when you're getting ready, your face is not bigger than your whole body, right? It's the same size. And the image formed is as far behind the mirror as the object is in front of it. Very simple. If you are standing here and the distance between you and the mirror is 3 meter, then obviously the picture that you're, or the image that you're seeing, that will again be 3 meter away from you, right? Like it will not be here. It will be exactly the distance that you guys are from the mirror. Okay. So it's virtual and it's erect. The size is always equal. If this is the size of the object, is the size of the image, A equals to B, always remember, and the distance is always same. Okay, now since we are talking about formation of image by a plane mirror, we should also talk about lateral inversion. It is also a very easy concept. It is that obviously when you are seeing yourself in the mirror, your right side becomes your left side, your apparent left side, right? So that is what lateral inversion is. So if you keep a mirror here, so let this be, and it will basically come like this, right? Like the image, if you keep a mirror at this point. So this is known as lateral inversion. So basically it's nothing that the part of the image or the part of the object that is closer to the mirror, obviously that part will also be closer when we see the image, right? So that's why this curved part is near the mirror and this straight part is away. Now its significance is that it's used in a lot of uh, cars, like for example ambulance, because what happens is that when you are seeing an ambulance, like even if there, by chance there's a problem in the siren and a car is here and the ambulance is behind it, even if the car can't hear it, from the rear view mirror what will happen is that the whole ambulance is written in laterally inverted way. Like M is obviously M can't be laterally inverted. So it is written like this. Why? Because when it gets reflected, you can see the whole thing straight. So yeah, so I just had to draw it in the opposite way. So anyway, so you'll be able to basically see the whole thing in this manner. So it has a lot of uses. Some letters cannot be laterally inverted, like M cannot be, T remains the same, O always remains the same. So yeah, so that is about a formation of image by plane mirror. It's very simple. Um, yeah. So before coming to spherical mirrors, we have to understand how, like why we call it spherical. It's basically, imagine a sphere. Okay, so it's not look like a sphere. Yeah. So if this is a sphere, now just imagine that we take some part of the sphere, like let's take this part, okay, this much part, and we are separating it and we are polishing this part, okay. So as soon as we properly make this part, like the curved outer curved part, opaque, and we polish nicely the inner part, let us use white, then it becomes a spherical mirror. So basically a spherical mirrors are those whose curved reflecting surfaces are said to be a part of the sphere. So we took this part from the sphere, right? So then when we polish one portion and make the other portion opaque, it becomes a spherical mirror. So you can take any part from the sphere and you can polish one side and you can make the other side opaque and it will become a spherical mirror. Now spherical mirror is also divided into two kinds of mirrors. One is concave mirror, another one is convex mirror. Okay. So what's happening here is concave mirror, it's basically a spherical mirror whose reflecting surface, noted here that we are talking about the reflecting surface here, which means the polished surface. So the reflecting surface is curved inwards, and that is it faces towards the center of the sphere. So if this is the center, this part is facing, like we have taken this part, right? So what we are doing is we are making the outward curved part the opaque part and we are polishing the inner part to be the reflecting surface. So when the reflecting surface is facing towards the center, it is called concave. Okay, and exactly the opposite of it, that is when we are taking, suppose we take the same part and we polish the opposite portion, that is if we take this same part and we basically polish this side, we make this side opaque and we polish the outwardly curved side, then this mirror is said to be convex. Okay, so a spherical mirror whose reflecting surface is curved outwards is called a convex mirror. A very simple example is that of a spoon. If you have seen a spoon, how does it look like? Looks something like this from the side at least. So it means that its inner surface, like the one from which we pick up the food, that is concave. Okay, and the portion that is outwards, that is the convex part. So we polish either and the opposite mirror, it can be used as. So the definitions are very important. You guys can pause it and write it down. Okay. So now we know how spherical mirrors have been made. Now we have to understand certain useful terms. Okay, so let this be a concave mirror only. Okay, so we know that it was taken from a part of a sphere. Okay, so it obviously has an imaginary center, which used to be the center of the sphere. It obviously has a radius because it was a part of the sphere once. Okay, so just keep these things in mind because we'll come across all this. The center of the reflecting surface of the spherical mirror is called the pole. Okay, so now we are talking about the center of the reflecting surface, not the sphere. So this is the reflecting surface. Let us call it AB. So if AB is the reflecting surface, we are saying that the middle of AB, like a point at the middle of AB, is called pole. Okay, simple. It lies on the surface of the mirror and the pole is usually represented by the letter P. Pole. Okay. So if you have a problem with seeing this color, I'll just change the color. Yeah. So this is the pole. The reflecting surface of a spherical mirror forms a part of the sphere, as I told you. Obviously, the sphere has a center. It's called the center of curvature of the spherical mirror, represented by the letter C. Center of curvature is not a part of the mirror. Obviously, when you look at the mirror, understanding the mirror ends here, but the center of curvature is like an imaginary point, right? It lies in concave mirror, it lies in front of it. In convex mirror, obviously in convex mirror, this is the, this is the polished or the opaque portion, right? So this is the pole, but the center of curvature here lies behind it because this is the reflecting surface. Here the rays will come. Okay. So now the radius of the sphere, which the reflecting surface of a spherical mirror is a part, obviously radius of curvature of the mirror, it is represented by the letter R. Okay. So this is basically R. Imagine a straight line passing through the pole and the center of curvature of the spherical mirror. This line is called the principal axis. Okay. So let us draw a principal axis. What does it say? That it has to be a straight line passing through the pole and the center of curvature. So something like this, and we extend it. Okay. The diameter of the reflecting surface of a spherical mirror is called the aperture. Note again that we are talking about the diameter of the reflecting surface. So technically, AB, the measurement of AB is basically the aperture for this mirror. Okay, so we came across center of curvature, we came across radius of curvature, we came across pole, and we also came across aperture. Okay. So now since we know all the important terms, we have to understand how images are formed using concave mirror. Okay, before that, let's just discuss what focus is, which focus is also an important term used here. Basically, what happens is that by experiment, it was found out that if you basically place, for example, a concave mirror and you throw light at it from infinity, it means that from a very, very, very far distance, you throw light on it. So if this is the principal axis, this is the pole, let's say, here is the center of curvature. Okay, so if you basically throw light from infinity, it is seen that after reflection, all of them pass through, it will get reflected. Yeah, all of them pass through a certain point somewhere between the pole and the center of curvature. So this point came to be known as the focus of the mirror. And it was found out that if this point is F, it was found out that CF equals to FP, which means that the focus of a concave mirror or a convex mirror is exactly between its center of curvature and pole. If this is the case, then it means that CP is also, if you remember from our previous discussion, it is also the radius, right? Here CP is equal to the radius of curvature. So this means that the focus divides the radius of curvature into two, right? So the length of the focus basically, this is basically half of the radius, right? Or radius is twice of the focal length. So this aspect is important. This we talked about concave mirror. When we talk about convex, it will look kind of the same. It will look the same, just that in this case, the rays will diverge, but they will be made to converge at the focus. That means that after reflecting, they will all diverge, but somehow, if extended, then they will all again converge at a similar point. So for a convex mirror also, all these equations like focal length being twice of the half of the radius, all these are the same, just that in reality convex mirrors diverge rays, so the rays will not be exactly meeting, they will be appear to be meeting at the focus. So that is the difference. Now we start with our discussion of image formation by concave mirror. So let's go one by one with the position. So first the position of the object will be at infinity. Okay. So as you can see, since this is a proper ray diagram, before discussing, just look how the rays are coming from the infinity and they are getting converged at focus. So basically what are you going to do is, so now since I'm drawing on a pen tab, it won't be absolutely accurate, but you guys should always use proper rulers and erasers for it, because the measurement is always has to be accurate. That's the whole point of ray diagrams. So let this be the principal axis, this be the pole, here is the center, this is a concave mirror, image is at infinity. So you just draw some rays coming parallel to the principal axis, because if the light source is from infinity, then by the time it reaches the mirror, it becomes almost parallel to the principal axis. So what's going to happen is that it's going to, by the law of reflection, angle I equals to angle R. Okay, so the reflected rays will always be in dotted form. Okay, but since I think it will be a problem for you guys to understand from the drawing, so I'm drawing both the incident and the reflected rays by proper lines. But remember, reflected rays always dotted lines. Okay, so you can see that even if it is not accurate here, it will be that. Okay, and don't forget to give the arrows, obviously they are very important, or else your marks will be cut. So all of them are getting converged at a common point known as the focus. So what are going to be the characteristics of this image? The position of the image will be at focus. It will be real, inverted, and diminished. Like it's highly diminished, so it comes as a point, like a small point. So it is real because there is actual convergence of rays and not imaginary. So the image will be formed real, inverted, and diminished. Now, when it is a point, there is no question of inversion because it is literally a point. In the next diagrams, you'll understand how the images are becoming inverted. Okay, so next position is beyond center of curvature. Okay, so we draw pole C, concave mirror. Now let there be an object AB beyond the center of curvature. They are saying, like, not infinity but not exactly close to the mirror, beyond center of curvature. So what is going to happen is that we draw one parallel ray. So this, you know that it will cross the focus, right? So let this be the focus, even if it is not accurate here, but just remember that CF will always be equal to CP, so please draw according to that. Okay, so if this is a parallel ray and it is coming parallel to the principal axis always, then it will obviously converge at the focus. And the next ray, what we are going to do is we are going to draw this ray passing through the center of curvature. Okay, so one interesting thing that you have to note, that whenever a ray is passed through the center of curvature, it is said that the ray will follow its exact path back. This means that at the point when it is crossing the center of curvature and getting incident at the point of the spherical mirror, it is forming an angle of 90 degree with the mirror, right? Like we know that any ray that passes through the normal, any light ray that passes through the normal of the mirror, making an angle of 90 degree with the mirror, will always be reflected along the same path, right? So in the same way, this ray is making an angle of 90 degree with the mirror, as a result of which its path of reflection is same. So angle I is equal to angle R, which is equal to 0, right? Okay, so like I hope you guys know that how we measure angle I or angle R, we measure it with respect to the normal, right? Like the angle it makes with the normal is the angle I, and the angle the reflected ray makes with the normal is angle R. So in this way, both of these are 0. So we made the ray pass through the center of curvature and now it went back to the same path. So can you notice the intersection here? So this is basically the image. So this is the object, we can name this as A dash B dash. So now what are the characteristics that you can see? It's obviously real because there are real intersection of the rays. It's obviously inverted, and also the third point, it is diminished, like the sizes are different. Okay, so the next one, okay, I'll just give a heading, object beyond C. Here it will be object beyond, sorry, object at infinity. Object at infinity. Okay. So now the third case will be object at the center of curvature. Object at C. Again the same process. B, C, we put the object absolutely on C, on center of curvature here. So again we draw a parallel ray which will again pass through F. We can't exactly put a ray through C, right? So what we'll do is we'll pass the ray through the focus. Now what it will do is, if I had drawn accurately, the image would have been something like this, if you can see. So that the ray which was parallel was focused at F, and the ray which was made to pass through F became parallel, and the intersection of these two rays came exactly below C, as a result of which the image was formed exactly at the place where we had kept the object, but it was real, it was inverted, and it was of the exact same size. Okay, so yeah, if I had somehow drawn it correctly, then it would have come to basically somewhere here. Okay, so same size. If this is AB, this is B dash, A dash, AB equals to A dash, B dash. The length is same, it's just real and inverted. Okay, so if you are noticing the pattern, that as and when you are moving the object towards the mirror, the sizes of the images are increasing, right? Like when you place it at infinity, the object came as a point. When you placed it beyond C, the object came diminished, but between C and F. Now it is the same size. So the next one should be a little bigger, right? So let's discuss that. What is happening is that when we are case 4, object between C and F. So now B, C, so now what is happening is that you are keeping the object here. This is your F. Again the same rule, and also so if it was drawn a little better, then it would have come at a point here somewhere. Okay, so just I'll just show you the actual proper ray diagram. So here basically the characteristics are the image is formed beyond C, the image is inverted obviously, but this image's size is greater than that of the object. So if we go here, we can see that The image's side is obviously greater. It is way beyond C and it is obviously inverted. So now our next case, as you have probably understood by now, is going to be at F, because C and F हो गया. Abhi this is, I think, the fifth case. So fifth case, object at F. So I think you guys have by now understood what it is going to happen, is that when you put an object at F exactly, the rays will for example go where? It will basically just go to infinity. So if this is the proper, yeah. So if you draw an image at, or if you place an object at F, then what's going to happen is that the objects are obviously, the image will always be formed at infinity. It will be real, it will be inverted, it will be highly enlarged. So it is exact the opposite of the first case that we saw. Okay, the last and the final one is the interesting one, and why concave mirrors have found its usage in day-to-day life is that object between P and F, which is pole and focus. Okay. So here P, C, F. So we are going to be putting the object at F here. So now what is going to happen? The interesting part about the sixth case is that the object placed between F and P will give an image that will be virtual. So let's just, so we know that it will pass through F, okay. So what's gonna happen is that we are basically going to extend this, because now a virtual image is being formed, okay. So what is gonna happen is that when we put the second ray, when we make it pass through the center of curvature, even if it is not passing, let's just for example take this as the center of curvature instead of this, and I'll just erase this part. I'll just show you the nice diagram after this horrific diagram. So yeah, so we have made, okay, don't forget to put the arrows though. Here this one, and here both the arrows will be like this only. And if we extend it, basically what we are getting is that we are getting an image here. Sorry, be straight. So A, B, then we have gotten an A dash, B dash. So what are its characteristics? It is virtual, it is erect, and it is enlarged, right? So if we take the proper ray diagram here, then you guys will be able to understand that here we've made one parallel ray. So we've taken like any arbitrary rays and all of them will basically just join and form the image on the opposite side of the mirror, which is virtual. So the characteristics are virtual, enlarged, erect image, and if they ask you the position of the image, it is just behind the mirror. How much behind the mirror? That has a calculation which we'll do in the next class. So for now, basically, just practice the ray diagrams at home. Use proper rulers, use accurate ray diagram, place the arrows in the correct way. Don't have to draw the normal every time and the angular, it's fine. Don't forget to mention the center of curvature, the pole, the focus, and try to make it accurate. Try to make it, like, if you measure it, if you always measure CF equals to CP, it will be that most of the time your diagrams will come accurate. Okay, so the next day we are going to be talking about images formed by convex mirror. We're going to be talking about the uses of concave mirror and the convex mirrors. We will be talking about the calculation of as to how far the image has been formed from the object. There's a formula called the mirror formula. So we'll talk about that. We'll talk about the magnification formula, which is how much bigger that the image was formed in these cases. And then we'll start with refraction. So that will be all for today. Thank you for watching.